Okay, so we talked in detail about oxygen transport, and now we're going to talk about the transportation of the other gas that we care a lot about in ventilation, and that's carbon dioxide or CO2. So, CO2 transport is the focus of this next couple lectures. So, you have three ways that carbon dioxide is transported. The total amount is around 45 to 55 milliliters per deciliter. Remember, a deciliter is just 100 milliliters. The first way is dissolved in plasma, just like or dissolved in blood. It's the same way that you could think of our oxygen, how we have a very, very small percentage that's dissolved. CO2 has more solubility, so it's a little higher, it's 8%, combined with a protein, which is 12%, or ionized as bicarbonate, which is the big way, that's 80%. So the first way that we talked about, the dissolved CO2, it has a much higher solubility than oxygen. So more of it is able to dissolve in a liquid than oxygen. So it dissolves in your plasma or in your intracellular fluid in your red blood cell. So just kind of know 8% of CO2 gets transported this way. That's all you need. 8% gets dissolved in either your plasma or intracellular fluid in red blood cells. The second way is that it's going to combine with a protein. So there's two proteins. You have CO2 plus a plasma protein, which is a carbamino compound, or CO2 plus your hemoglobin, which is a carbaminohemoglobin. For your flashcard and for your knowledge purposes, just know that 12% of CO2 combines with a protein. I'm not going to make you know these or use these different protein terminologies. So just 12% combined with a protein. The process that I am going to examine you on, and that I do want you guys to really understand well, is this ionized as bicarbonate. This is the big way that CO2 is transported. So this one we're going to dive into a little bit deeper, and I want you guys to feel pretty strong in this concept. So we're going to start with this equation here, okay? And I know it looks intimidating, all right? I was not a huge fan of chemistry when I took it, but it's really not so bad when you break it into small parts. So let's start here. CO2, or carbon dioxide, which we're all familiar with, combines with water in your body. And we know this because most of our body is made up of water, right? So the CO2 is going to be in your body and it's going to combine with H2O or water. When it does this, it forms H2CO3, which is a weak acid. This compound does not want to stay together. Okay, this is not a compound that ever wants to be together. So what it does is it dissociates. And what I mean by dissociate is that it'll come together briefly, but then it wants to break back apart. And so it's got these arrows here. If you look, they go both directions. So when this breaks apart, it's either going to break apart into CO2 and water, or it's going to break apart into something called bicarb, which is this HCO3 minus, that's bicarbonate or bicarb, plus H plus. And H plus is an acidic ion. It's a positive ion commonly associated with acids. So here you have your H2CO3, does not want to be together, will come together briefly, but then it's going to want to break apart. And it's either going to break apart into bicarbonate and H plus, or it's going to break apart into carbon dioxide and water. And there's different things that are going to determine whether it breaks apart this way or it breaks apart this way. All right, and we're going to go over this a couple of times, and we're going to go over this in class, and I'll probably come up with some version of a diagram. Try to keep your guys' excitement in check. I know you're just on the edge of your seats, but this is a big concept for CO2 transport, so we're really going to dig in here. Just know that this is a rapid reaction. So it's moving this way all the time. It's moving back this way all the time, this way and back. All of this happens very rapidly, and it happens in the red blood cell. You guys do not need to know this carbonic anhydrase catalyst. I'm not going to quiz you on that. I probably should have deleted that out of there. So just in your mind, or if you print these, just X that off. Just know that this is a rapid reaction in the red blood cell. So this brings us to the Bohr and Haldane effect. So if we're talking about the Bohr effect, we'll start there. This is going to occur in the peripheral tissues. So I want you to think about the tissues in your toes, your organs, like all the things in your body are associated with the Bohr effect. And I want you to kind of link in your mind Bohr effect, tissues, high CO2, low O2, and a right shift on that oxyhemoglobin dissociation curve. Okay, that's why they're all in the heading. You can kind of link them together in your mind. So again, ionized bicarbonate is about 80% of CO2 transport. The reaction that takes place in the red blood cell at the tissue is that the CO2 is going to combine with water to make this weak acid, and it's going to dissociate into H plus and bicarbonate. After it dissociates into these two compounds, that H plus is going to bind to your hemoglobin. So same hemoglobin that we talked about before, that's a bus for a lot of different gases, a lot of different things. It's going to bind to the hemoglobin. The hemoglobin's going to act as a buffer, and that's just important from the fact that CO2, because it creates this H plus ion, creates more acid. So the hemoglobin acts as a temporary buffer. We're not going to go into that a ton, but just throwing it out there. So the H plus, big takeaway here is the H plus is going to bind to the hemoglobin. The HCO3, or the bicarbonate, transfers out of your red blood cells. So you've had this reaction where this dissociated to the H plus and the bicarbonate. The H plus bound to a hemoglobin. The HCO3 goes out of the red blood cell. It's replaced by a chloride ion, and this is called the hamburger phenomenon. Now, as far as you in your life, the hamburger phenomenon only comes up in a random, like trivia style way. I think the last time I heard of this being quizzed for the respiratory therapist was it's something called the sputum bowl, which is kind of like the Jeopardy of respiratory therapy. So you can memorize it for that, but just know that this guy kind of buggers off for a while. It leaves the red blood cell, a chloride ion comes in, it balances the charge, and this is the hamburger phenomenon. I personally, from a biochemistry standpoint, am not quite sure why this has to leave and the chloride has to come back in. But I can tell you it's called the hamburger phenomenon, and that's about all you need to know about that portion of it. The part that is really important that you take away is that the H plus is going to bind to the hemoglobin. So the Bohr effect happens because we are in the tissues, we have high CO2, we have increased CO2. That is going to decrease hemoglobin's affinity for oxygen. Okay, so if you come back up to this title where I told you the things to kind of know, Bohr effect occurs in the tissues where we have high CO2, low O2, and it's a right shift on the oxygen hemoglobin dissociation curve. So because you're in the tissues and you have this increased CO2, you're going to decrease hemoglobin's affinity for oxygen, which means that it is going to unload oxygen from the hemoglobin into the tissue. That's where you need that oxygen. You want to be oxygenating your tissues. And the CO2 is going to be picked up by the hemoglobin and transported to the lung, which is what you want to happen because that's where it needs to be exhaled. So the CO2 gets picked up in this fashion up here. Okay, so the CO2 gets picked up because the red blood cell picks up the CO2, it combines with water, you get this weak acid, it dissociates, this H plus is going to bind to your hemoglobin, this guy's going to get kicked out of your red blood cell for a while, and that H plus, or that H hemoglobin, HHB, H hemoglobin, is going to now go back to your lungs. This is where the Haldane effect is going to occur. So we have had our tissues create one version of this reaction. Now, when this hemoglobin gets to our lung, the Haldane effect is going to take place. So you have high oxygen, right, which is going to want to change the affinity of that hemoglobin again, and it's going to knock that H plus off that hemoglobin. So this HB is your H plus hemoglobin. Because you have the high oxygen in your lungs, it's going to knock that H plus off your hemoglobin. So now you're going to have H plus, and then that HCO3 is going to come back into your red blood cell. That's going to combine to form that H2CO3, which we know does not want to stay together. That's going to dissociate into water and CO2. So the high O2 knocks the H plus off the hemoglobin. The H plus joins that bicarbonate, which is dissolved in the plasma, to form that carbonic acid, the H2CO3. The H2CO3 dissociates and forms CO2 and water, which is then exhaled from the lungs. So we talked about the reaction happening the one way, and now it's going the other way. And the things that are making the difference are having that high O2 and that low CO2 in the lungs have kind of reversed the reaction that happened in the tissues. So the Haldane effect happens because of increased O2 will decrease the hemoglobin's affinity for the CO2, right? So that's what bumps that H plus off of the hemoglobin and allows the O2 to get back on. So then your O2 binds readily to your hemoglobin, displacing the H plus to allow for that H2CO3 to form and create CO2 and water to be exhaled. Oxygen binds readily to the hemoglobin, directly displacing the CO2 that is bound in the form of that carbaminohemoglobin, allowing that to be exhaled. That's that other way that it gets transferred by that 12% by combining to the protein. So this is the other way that it gets exhaled. And I realized that probably listening to me say this out loud was like, what? So, tools that you guys have, I have a further explanation of this underneath the exam review tab. There's a content folder that says further explanation. Underneath there, there's Bohr and Haldane, where I have written this out again, because I think listening to this the first time through is probably just like not the best way to absorb this particular concept. So I took the time to write it out in a further explanation under the exam review tab. The other thing that we're going to do is when we get into class, I'm going to use a diagram and show the biochemistry of how this works. But the overall principle, if we're going back here, is that this reaction is a reversible reaction. You have CO2 plus water, which goes to this weak acid in the middle, H2CO3, which is carbonic acid, right? But this weak acid, this does not want to stay together, so it either dissociates this way or it dissociates this way. Now, in the tissues, it's going to dissociate this way. And the reason is because it has low oxygen, high acid, and so this H plus is going to bind to the hemoglobin because that's what the hemoglobin is going to want, because the affinity for oxygen at your tissues is going to be low. And if you think about why that would happen, is the tissues is where you're going to need to offload oxygen. It's where if you're following the bloodstream from your lungs down into your tissues, it needs to now unload the oxygen that it's carrying. And it does this because this high acid makes it not really want that oxygen anymore. So it dumps its oxygen. It now has 4 open seats that pick up this H plus, pick up this CO2 directly, like 12% is going to pick up CO2 directly. And then it's going to travel back to your lungs. When it gets back to your lungs, because of the high oxygen content and the low acid content or the low CO2 content, it's going to want this reaction to then come back to this H2CO3 and dissociate this way. So that the same thing is happening. This is coming together to form the H2CO3, but now it's going to dissociate into carbon dioxide and water. And it's doing that because you have a high amount of oxygen available. So now that hemoglobin really wants to pick up oxygen, because that positive cooperativity, the more oxygen available, the more oxygen it wants. And so now it's bumping off this H plus so that the reaction can happen and go backwards the other way. And how you can kind of keep it straight in your mind is we exhale CO2 and water. That's what we exhale. So this is happening at your lungs. This is your Haldane effect. And at your tissues, you have this happening. This is your Bohr effect on this side of the equation. And again, we're going to go over this in class, hopefully with a diagram where I can try to find an easier way to explain it. But it's not as complex or confusing as it probably sounds in this recording. It's just, this is the first time we're going to layer this so that you guys feel comfortable before the exam. So this is layer 1. I hope that it landed a little bit, and then we will continue to work on it. Here are your lecture questions. As always, email me if there's anything you're confused about or that I can help you with.